Okay, so do we all have the data open? It is on web courses under data for class.
Is it under files? Or modules?
Who all has, just out of curiosity, who has SPSS on their computer so they don't have to do this ridiculous stuff that I'm doing?
We're all doing that ridiculous stuff.
You're all using UCF apps?
Yeah.
Ugh. It's the worst. If you'd rather use Stata, you're more than welcome to use Stata. Nothing that I'm going to do can't be done in Stata. Faster and easier. I use Stata. I hate SPSS so much. But since that's what the department gives you guys, that's what we're using. So here we are. Okay, this is the same data we were just working with to calculate a correlation. Let's do a few things here really quickly. First, let's just calculate our correlation. Analyze, where's my correlate, bivariate. We're going to correlate these two things. Apparently I can't select them both at the same time because I'm, whatever. Okay, so we look at this correlation, and the correlation should be what?
0.65.
0.657, yeah. And let's do another thing. Let's look at a scatter plot of this data. Anybody know how we do a scatter plot in SPSS?
Probably graphs.
We go graphs, and then,
Probably chart building.
no, chart builder's terrible.
Legacy.
Legacy dialogues.
Hey, look, scatter/dot.
Where?
Now.
Yep. So we will do a scatter plot. We're going to do a simple scatter plot. Define that. We're going to put publications as the y-axis and time since PhD on the x-axis. I wonder, can we? No, we can't. I wondered if we could add the trend line here, but we can't. So anyway, we hit go. And all right. So here's our scatter plot. And does anybody know how to add a trend line? So if we double click on our scatter plot, we'll open up like this chart editor. Don't need that. And then we can go elements, fit line at total. If you say fit interpolation line, it's going to give you something else. Fit line at total is your basic kind of correlation line, right? We want a linear one. And I'm wondering, can we? Oh, we can't. It might just throw the program right in there. Close. Oh yeah, there it is. So there is our formula, right? Why won't it let me move it? Psst, psst, psst. Oh, it makes it stick kind of on that line. Well, okay, fine. I believe that we can close this and it will pop up here now. Yes. So let's have a look at this. Let's break down this basic algebraic equation. What does a regression equation tell us?
I mean, it tells you like you can calculate expected values, I guess.
Yeah, so this line represents what? Say that again? Line of best fit for the data. It is what the best prediction that we can give, right? And the cool thing about a regression equation, I mean, digging way back into your like 5th grade math or whenever you guys learned how to do slope. If you have this equation, you can find a value for any given person, right? And that's what regression is doing. It's allowing us to find a value for any given person. The value right here, walk me through, what does this mean? That equation, can you guys read it? It's kind of small. Let me see if I can make this a little bit larger.
By the way, we also have like nonlinear regression. Is that a thing?
We will get there, but yep.
Okay.
I don't know that I can make. Does this change it? Nope, that doesn't change it. Okay, so we have an equation here. And what does that equation tell us?
The equation?
Yeah, like what does that mean in terms of regression? What does it mean for us? Or in terms of our data, or like why do we do a regression equation? What's the purpose? This actually is going to become incredibly important later on when we want to know intercepts and so on. And when I said at the beginning of this class, like you teach a class and then you think like, oh, I wish I would have spent more time on this. That's what I'm talking about now. I spent the entire lecture last year talking about correlations and neglected to spend as much time as I should have on regression. So we're going to spend some time talking about regression. That equation tells us that when time to PhD is 0, our intercept, right? Y is what? 4.73. Exactly. When time to PhD is 5, what should Y be?
15.
About 15. Can somebody figure out exactly what it should be? If your time to PhD is 5, what should Y be? What is our best predicted value of Y?
1.98 times 5 plus 4.7.
Perfect. That's how we find it, right?
14.
Like you take a value, you multiply it, and then you add that. And so our constant is always what? The constant always represents what? The intercept always represents what value? The value of Y when X is 0. This is going to come into play later because we're going to center X, right? And when we center X, that makes our average score of X 0, right? And it makes what our intercept? Our intercept becomes the average score of Y when X is 0, right? Because the intercept is always the average score of Y at some value of X. And in this case, the value of X is 0, but it's uncentered. If we were to move this, just out of curiosity, let's do something here. So if our value of X was actually centered, I wonder if we can do this math in our heads or if we need to actually figure this out. What should our intercept be?
About 25.
25. That's an about-ish. Is there a way to figure that out? It's not 25, by the way. I'm just going to throw that out there.
Is it close to 25?
It is close to 25, yes.
I'm just looking at it. Would you like
Let's think about this for a second.
equate
Yeah.
two equations for a line, like set them equal to each other, and then calculate?
You don't even have to go that far. If our best guess right now, assuming we know that someone's PhD was attained at 0, and that means that the average Y is 4.73 or whatever, assuming 0 years of schooling. What do we need to do to move that up to what was our average of X? Anybody remember from that Excel file? 7.666666667, right?
So yeah, exactly.
Okay. So if that is our average score here, is there a way to figure out what Y should be? Plug it in. Okay. So plug it in once.
Oh, sure. Right. You on it, Matt?
19.89. That is what? 7.677 times.
Yeah.
Plus 4.73. So
19.
it's 19 point something. Okay, let's do something else real quick here. Let's go like this. Let's go
19.7.
analyze, descriptives, explore, and let's just look at the mean and standard deviation of these two variables. Did you see what I did there? Analyze, descriptives, explore. And so we have our mean here that we just said, 7.67, right? And what did you say the intercept of Y would be if X was set at 0?
About 19.7.
And that also happens to be the mean of Y, right? So when we center X, our intercept becomes just our best guess of what Y is, assuming that we have no predictive value, X times 0, right? Or the slope times 0. And that means that our best guess of what any one Y is just going to be the average, right? Like it's essentially saying, if you think about a regression equation, you have a slope of 1.98 times 0 plus some value, right? And in this case, that some value becomes the average, right? So in our height example, if we did not know what a person's biological sex was, and we could go either way, right? Like it was centered right in the middle. It could be either up or down. Then it's going to be the slope times 0 plus our best guess, which is the mean of Y, which is always our best guess. And that is, in that case, 5 feet 6 inches, right? Yeah. So this is going to become, I just want you, I want to familiarize you guys with this right now because it's going to become increasingly more important as we move on. Just then to highlight a few other kind of small things. This formula is predicting this line, but in truth, nothing ever fits this line perfectly. No data set fits this line perfectly, right? So what we're actually doing is we also have a thing that gets tagged on the end here called what? Error or residual, right? And the residual is the distance between any given point and where it actually is predicted to be on the line, right? And so when we're talking about whether it's sums of squares or residual or r squared, all of that has to do with the extent to which these dots are spread out on this line, right? So you could have a slope that looks just like this and has an r squared that's 0.439, or a slope that at least that's 1.98, right? And that slope may have absolutely no value because the dots are too far spread out, right? That slope value is the value of the predicted mean minus the actual mean divided by the standard variation in the data set, right? So any slope value winds up being kind of that piece of it. If it's really, really tight, then you wind up having a strong statistically significant slope. If it's really, really loose, if your variance is quite high relative to your predicted value minus your actual value. So you can think of it in terms of a basic z-score, and this is how we get to t, right? That t is a measure of the average predicted value minus the average actual value divided by the variability in values. And if your numerator is, or your denominator is really high, your t-value becomes increasingly smaller, right? And as that denominator gets smaller and smaller and smaller, the t-value gets higher and higher and higher, right? Does that make sense? All right, cool. I'm trying to think of what else I wanted to talk about here. Let's do this. I'm going to pull up your guys' homework here real quick. So if you guys want, you can go in here. You can see all of the modules for the rest of the semester. I post a link to the video here. There's data for class. Make sure that when you guys come, you download the data for class, right? Oh, I know what I wanted to talk about. So here's your homework for this week. There are 7 questions. Normally, everything I want you guys to turn in should be in like an APA style format. Not for this week. Don't worry about that. You can just type things up and include an Excel file to calculate this stuff. But so let's see what these are. This is actually, I don't know that number. I'll leave number 3. I won't say it. I told you guys what an easy mathematical definition of a Pearson correlation is, right? Yeah. So we'll hold off on that. Based on the equation, what is a predicted value? Oh yeah. We've covered that. What is the difference between the predicted value and the actual value called? We've covered that. And why is the correlation between y hat, the predicted value, and x equal to 1? Anybody know the answer to that? I'm just going to throw it out there. Why is the correlation between y hat, our predicted value, and x equal to 1? Let's flip back over and look at this. I think it's an interesting point to think about, to ponder. Why is the correlation? Let's do something. I'm going to do this in, actually, do I have? I do have. Okay, so let's go analyze, correlate, bivariate. Let's remove publications. I don't know which one of these is the right one. Let's try this one. This might. It's the wrong one. Analyze. Is this the right one? I don't have any names on them. There we go. So this is the correlation between time since PhD, our x value, right? And it says unstandardized predicted value. That is our residual, right? Or I mean, yeah, it is. It winds up technically being the residual. That's correct. So it is the correlation is equal to 1 between these values here and this line. Why is it 1? Yeah, that's exactly right. Every value of y hat falls perfectly on that line, right? If we go analyze, graph, legacy subgroups. Our dots, our predicted values, all fall perfectly on that line, right? And so, I mean, it's just highlighting the point that those predicted values are what X thinks they should be, right? Does that make sense? And so the residuals that you get from any regression model are actually the discrepancy between where y is and where it should be on that, along the x-axis, making it essentially the perfect score for what it should be at that given point. Does that make sense? All right. I don't think I have anything else to talk about today.
I have a quick question.
Shoot.
You've mentioned this a couple times, I'm going to write it down. The difference between the correlation coefficient and the slope of the regression line. Or, I don't know if it's the difference or a difference. Is that correlation coefficient standardized?
Yes.
The difference, a difference?
That is the difference, yeah. And the correlation coefficient. So let's do this, actually, real quick. Let's go analyze. You can do that. Like, this only holds true, just FYI. What I'm going to show you right now only holds true in a bivariate analysis, because as soon as you move into a multivariate analysis, you no longer just have 2 circles, right? You can have 3 circles or 4 circles or 5 circles, and then you have more overlapping variance. You have variance that overlaps, you know, with multiple different Venn diagrams. So, but if we do it just in this, we can go regression, linear, publications, HD, and where's my? Do I actually have to select provide a standardized? I don't know if I do. I think they maybe give it to us. Yeah, so here is our standardized correlation coefficient, right? 0.657, 1.983. And so in this model, at least, these 2 things are exactly the same, right? Like the correlation coefficient and the regression coefficient. Now, as soon as you add another variable, it doesn't hold up. Though, why don't we have a correlation coefficient for our standardized beta? Or I mean, I'm sorry, an intercept for our standardized intercept. I don't know if I've ever used that word before. But why don't we have a coefficient for a standardized intercept? It is a constant, but it's more important than that. We've been saying when you set the mean of this to this, then it becomes the mean of that, right? We've just standardized 2 variables, made them both what? What does their mean? I'm sorry. When we standardize 2 variables, their mean is what? It is 0, right? When you set, so if you have our equation of 4.73 plus 1.98 times x, if in 4.73 is the mean of y when x is 0, assuming we standardize everything, what is our mean of y? If we know nothing else, what's our best guess for y? If y is a z-score.
You mean the 19 would be good?
No. Once we made y a z-score. 19, actually, so let's go back to that. Why was 19 our best guess for y? Because that was the mean. Apply that to z-scores. What is our best guess for y?
Oh, it would be 0.
It's 0, right? So if you think about your regression equation, then if x is 0, which is the mean of x, then our best guess for y is just the mean of y, which is, in a standardized score, 0, right? Absolutely. So your intercept is always the average of y when at the 0 value of x. This becomes actually even more important when we start talking about, let's do something. Actually, I'm going to use Stata for this. Sorry. So if we go tab sex, cool. So it's just a simple bivariate variable. Let's go regress affectability on sex. We have a statistically significant coefficient here, right? Can you guys see this? Let me see if I can make this a little bit bigger. View. Make text bigger. Can I just... There we go. Okay. So we have... Somebody explain this correlation to me, or this relationship here. What's going on? I'm sorry, so in this data set, women are coded as 0, men are coded as 1. So the outcome variable is the mean, or I mean our intercept is the mean of our outcome variable when x is set at 0. So if x is coded 0 and 1 with 0 being females, what is our constant? What does that tell us about our data? Yep. The average of the outcome is 1.97 for the 0 group, right? Because we're saying like x times 0. So that's for our 0 group. If we took that times 0, so we can test that. Let's go sum alls if sex equals 0. That looks pretty close, right? Even cooler though, since it's just simple linear algebra, what is the mean of men? So you're saying it is this value?
Yes.
Minus this value? Or plus or minus this value? But 1.8765535, we can check that work. Again, stats is just simple linear algebra for the most part, right? Like everything that we're going to do in this class, at least, is simple linear algebra. One of the great things about this is now you can do an ANOVA, you can do a regression, you can do a t-test, you can put those in a regression table, and people can compute what every other thing is in that table, right? So if you just know this, you can figure out the mean of men and the mean of women. What is the relationship between ANOVA, regression, correlation, t-tests? Is there any difference in these things? The names are different. You are right. Let's do something here quick. Oops. Comma. Okay, so in Stata you have to put beta to get the standardized relationship, right? So there's our standardized relationship. Now let's go And even though this is just a bivariate, or I mean just a dichotomous variable, we'll still have a correlation that is equivalent to our slope, right? And here's something even cooler. What is the relationship here between this regression model and a t-test? What does this coefficient tell us about men and women? The difference between men and women. So if we go t-test alls by sex, our slope was 0.0984135, and if we come down here, the difference in our two means, here's our means that we've already calculated, is 0.0984135. All that slope is a difference between groups, right? In regression, it's a difference between, it's the amount of rise over our run in x. And in this case, our x is 0 and 1, right? So we move 1 unit, we move up that much. The same holds true with every type of regression that you're going to do, though, right? So if you have, in our data that we've been toying with, if you add another year to PhD or another 3 years to that PhD, then you wind up just multiplying whatever that coefficient is times whatever the number is, right? And it will tell you the difference at any given time between publications at this year and publications at some other year. Of course, that's the predicted difference. Oh, no, it's the actual difference plus, because the predicted difference is actually the mean, right? So it will tell you exactly what the mean difference is between those years. Make sense? Technically, then you can use that if you wanted to do a t-test between like this year and this year, like if you wanted to jump across years. Yeah, does that make sense? The take-home message, I think, is correlation, t-test, ANOVA, regression, all the exact same. Oh, and not just all the exact same. Here is our t, right? 2.7539, and if we come up here, we also get a t for our coefficient, 2.75, right? And if we do this, ANOVA, alls, sex, we get an F of 7.58. And how is F related to T? Anybody know? When you think of an F table, statistics loves to do this. Many fields of statistics don't like, or like many equations, statistics don't work if you have a negative value. Can you have a negative T value, negative Z value, a negative F value? No, you'll never see one, right? Like the table starts at 0 and goes like this, right? Same with chi-squared, which is really just a different form of F. So if we go 2.7539, and we just square that, 7.5839, T is nothing more than F squared, right? We use the exact same sorts of statistics. And all of this falls under something called what? Anybody know? This kind of broad framework that we use to think about regression, ANOVA, t-test, correlation, all of it. Nobody knows? I'm waiting. I'm going to wait the full 20 seconds.
It all involves variance.
It all involves variance, but there's a framework for statistics that all of these things fall under. There are...
You mean like null hypothesis?
No, but yes. I mean, null hypothesis actually falls under this framework also. I'm sorry. There's a broad umbrella term that encompasses all of this stuff. Frequentist falls under this also.
What's it called? Not this
Oh, wait. I thought I heard it.
Statistics.
No, it starts with a G. There we go, general linear model. The general linear model is this basic linear model where we are looking to plot a single line through our data, and we use squared deviations away from that line to figure out the magnitude of effect of anything, any two or more associations in a data set, right? We have another, the general linear model falls underneath something, a broader umbrella that we aren't going to do in here, called the generalized linear model, where nonlinear relationships are transformed into linear relationships to try and make more sense of them, and then transform back into nonlinear relationships. But, yeah. Okay, that is now all that I have for today. Any questions for me?
I think, let me just double check. I think on the home page on the courses there was a link that was,
There's what?
a link that was not working. I think it was the getting started.
I wonder if they changed
Yeah.
something.
Page not found.
I don't know. Well, I can add that link
So I
in,
could
but
get
no,
started.
it's in modules anyway. So
Oh, okay.
I just need to fix that. All right. Why do we do inferential statistics?
That's fun.
What is the purpose of inferential statistics?
Fun.
To have fun? To predict. Yeah, right. To predict why, what? I mean that in the sense of the word, not the letter.
Because it's hard to know exactly.
Yeah, it's to give us a best guess of why someone isn't on that line that they should be on, right? And the magnitude of certainty that we have around the fact that they're not on that line. Right? Does that make sense? All right, that's it for today. Have a good day. If you have any questions, let me know. Otherwise, homework is due next week. Turn it in Excel and piece of paper. So, no other questions? Cool, we're done.